meeting, and the topic is very interesting because neuroprotection is very important in pharmacotherapy for today. And in this case, I would like to tell a few words about sigma-1 receptor. It was discovered about 30 years ago, but knowledge about this receptor developed very quickly. And the last 20 years, all meetings which discussed sigma-1 receptor, the title was Sigma Enigma. And today I want to disclose this enigma. And I must tell you that enigma is that sigma-1 receptor is not a receptor, it is a ligand-dependent chaperone. And its role in neuroprotection I'll try to explain you today. So, very quickly, but very quickly is impossible. First slide, please. Sigma-1 receptor, gene of sigma-1 receptor localized in 9 chromosomes, and it codes 2 amino acids. One of them recognized as canonical form, and another one have no possibility to ligand any compounds. Next slide, please. No. Sigma-1 receptor have 2 hydrophobic transmembrane domain. It's able to there is capability to dimerization, and in amino acid sequences we can find some place for binding. For example, binding cocaine, binding cholesterol, binding galoperidol, and some other substances. That's important because different sites for ligand interaction provide many properties, especially neuroprotective properties. Sigma-1 receptor peptide, this peptide expressed in different organs, in liver, in brain, in different area of brain. It's important too. Then, endogenic ligand. That's very interesting to correspond the information which I give you now with previous topic, because previous speaker said about neuroprotective properties of neurosteroids, and to my mind it's very important that progesterone, pregnenolone sulfate, dihydroandroepisterone are endogenic neurosteroids which are synthesized in brain, in mitochondria. And these compounds are endogenic ligand to sigma-1 receptor. A few years ago, as endogenic ligand was identified dimethyltryptamine. It's important too because it's metabolite of catecholamine. Next, some synthetic ligands. Prototypic ligands, derivative of benzomorphan, pentazocine, SKF, and some other compounds which are able to bind to sigma-1 receptor. And now most important, what can do sigma-1 receptor? Sigma-1 receptor localization is in endoplasmatic reticulum. So it's not localized in surface membrane. In endoplasmatic reticulum, sigma-1 receptor is associated with another chaperone which names BIP and peptide ankyrin. Together they close the receptor for inositol 3-phosphate. And when we have stress situation in cell or ligand activation of sigma-1 receptor, this complex dissociated and open IP3 receptor for interaction with inositol 3-phosphate. It's a very important feature because after this we have a calcium transport movement from EPA to mitochondria. It's one of mechanisms to restore energetic deficit of mitochondria when we have cell stress. One mechanism. Another mechanism which is linked with sigma-1 receptor, it's its capability to move from endoplasmatic reticulum to plasmatic membrane. It's very important because this peptide sigma-1 receptor or chaperone is surrounded with lipid raft, and it moves from EPA to plasmatic membrane, being surrounded with lipid raft. It's very important because lipid raft, which consists of cholesterol and sphingomyelins, are the basis of a lipid raft in plasmatic membrane, which keep peptide, protein, receptor, ion channel, enzymes, conformation. It keeps enzyme, it's a carcass phospholipid, cholesterol and sphingomyelin. And it's very important that sigma-1 receptor move from EPA to plasmatic membrane, being surrounded with this lipid raft. And here, in plasmatic membrane, sigma-1 receptor is able to contact and make protein-protein interaction with natrium channel, sodium channel, chloride channel, especially GABA, kalium channel, NMDA receptor, very interesting interaction with NMDA receptor. When we have a small concentration of glutamate, sigma-1 peptide help to increase this process, the remediator process, and this lead to increase of synaptic association, synaptic links. But when we have over expression of glutamate and overloading of calcium, sigma-1 receptor protects this process and decrease calcium influx in cell. Very important that sigma-1 receptor can interact with phospholipase C. In this case, the cascade of deacylglycerol and IP3 start again, and all processes which depend on calcium work in cell. Simultaneously, sigma-1 receptor switch on calcium-dependent ATFase, and excess of calcium is go out from the cells. So all these processes may be considered as calcium balance regulation. So, in summary, we can say for today, our knowledge for today permits to conclude that at the NMDA level, we have two processes, potentiation and suppression, calcium suppression, IP3 potentiation, kalium suppression, chlor suppression, dopamine suppression, noradrenaline potentiation, acetylcholine potentiation, NMDA neuron potentiation, serotoninergic neuron potentiation, and dopaminergic neuron in mesencephalin, two processes, potentiation and suppression. I want to pay attention a little bit more for lipid phase. As I tell you that sigma-1 receptor move from EPA to plasmatic membrane in lipid raft. What does it mean? You know that sphingomyelin, which is a part of this lipid raft, the synthesis includes a formation of ceramide. Ceramide is a very active intermediator, and when we have disbalance in its production, we switch on all processes which lead to cell death. inhibition of BCL2, inhibition of respiratory complex and mitochondria complex 3, activation of caspase, which lead to cell death. So, in any cell stress processes, we have free radical attack for plasmatic membrane, and in this case we increase ceramide formation, and it's very important that when we have transport of sigma-1 receptor to plasmatic membrane, we have reconstruction of plasmatic membrane using phospholipids, which are synthesized in endoplasmatic reticulum. So, this is a few words about sigma-1 receptor. Very difficult to decide what is antagonism or agonism when we're speaking about interaction with sigma-1 receptor, because you see very different effects, potentiation, suppression. And Hayashi, the Japanese scientist who work in the United States, and many very good article was published from his lab about sigma-1 receptor, suggest to consider all interaction which lead to dissociation sigma-1 receptor from BIP chaperone, consider as an agonist effect, and all interaction which is not able to do this dissociation consider as antagonist. And really it's confirmed in experiment with cell stress. You can see that cell stress lead to dissociation, and some typical ligand lead to dissociation of sigma-1 receptor from BIP chaperone 2. And in this case, pentazocine plus pentazocine, SKF 147 plus are agonist, and such compounds, for example, as galoperidol, is antagonist. Now, I will tell you about new Russian medicine afobazol, which was developed in our institute and now are in practice in Russia as anxiolytic. Why I will speak about afobazol? Because afobazol is the first medicine which introduced in medicine practice in the world, which interacts with sigma-1 receptor. Afobazol is a derivative of mercaptobenzimidazole, and it has a pharmacologically suitable interaction with sigma-1 receptor. Very important that incubation of sigma-1 receptor with afobazol lead to its movement, its transportation from EPR to plasmatic membrane. You have see here the results of confocal microscopy. This green color at the surface of cells means that movement have been movement of sigma-1 receptor. In the United States, in South Florida, California, in South Florida University, was done several experiments which prove influence of afobazol on calcium balance using some antagonist of sigma-1 receptor. You have seen here the ischemia acidosis model and increasing influx of calcium into cell. Afobazol prevents this increase, and antagonist decrease effects of afobazol. The same situation in model of ischemia, the same situation in model of inflammatory model. So you can see that afobazol decreased microglia transport, which is attracted by ATP, and antagonist of sigma-1 receptor prevent this effect of afobazol. All the slides prove that afobazol works through sigma-1 receptor. And this slide shows that when we add beta amyloid, afobazole have protective effect too. All this work was done in the United States. In our first experiment, we developed afobazole as an anxiolytic. And you see in this experiment that is behavior of mice, bulb C and C57 black 6 in open field. Why is this to strain? C57 black 6 is not sensitive in this test to stress, and bulb C have a freezing reaction. You can see that no effect afobazole produced to C57 black 6 mice and activate the behavior in bulb C mice. Benzodiazepine in this case gave sedative effect in C57 black 6 mice. GABA receptor, you know about this, previous lecture describes this receptor. I will not stay on this. But what is important? Stress, when we have the reaction of freezing reaction of anxiety, we have the decreasing and binding capacity of benzodiazepine receptor. And in case of bulb C mice which have freezing reaction and anxiety in open field, you have the decreasing of binding. And C57 black 6 mice which are not responsive for this stress, no changing in binding exists. But more severe stress when we work with predator, you have seen decreasing of benzodiazepine binding in both strains. In all these cases, afobazole prevent this decreasing. So it's a mechanism of its anxiolytic effect. How it will be? We believe that sigma-1 receptor working with afobazole is go to GABA A receptor and restore its conformation, improve possibility to bind endogenic ligand. So it's a new mechanism for anxiolytic effect. But direct data about neuroprotection we can receive in vitro. I will show you several models with peroxide. You can see the mod cell survey after addition of H2O2, and the same we have after in model of glutamate toxicity. Afobazole have a protective properties. The same another type of experiment, stress lead to the decrease of brain-derived neurotrophic factor. It's very important, and you see in all cases, in all structure of brain, afobazole restores this level of BDNF. It's very important for their protection. In vivo experiment, model of brain infarct after middle cerebral artery occlusion in rats. You see that in 1 milligram per kilogram and 0.1 milligram per kilogram, afobazole prevent cell decrease size of infarct. In a model of hemorrhagic insult, hemorrhagic stroke, afobazole prevents mortality of animals. And even when we make a model of second stroke, in old animals which survive in previous experiment. This effect, we have two. Afobazol prevent and decrease mortality of animals. Very interesting, the conception that haloperidol is antagonist of sigma-1 receptor and afobazol is agonist. We perform experiments to investigate is able afobazol to decrease extrapyramidal disturbances, which is one of the side effects of haloperidol. And you can see that afobazol twice decrease extrapyramidal movement disorders, which is effect of haloperidol. In other experiments, morphine withdrawal syndrome. You see, this means increasing of anxiety after morphine withdrawal. Afobazol decrease this effect of morphine withdrawal. And I can make a conclusion on basis of this experiment that sigma-1 receptor is ligand-dependent chaperone which provides cytoprotection and different disorders related to endogenous changes and exogenous influence. Only one problem which should be solved, but it's a very important problem. I think that the person who will discover this will be Nobel Prize. It's not understandable the mechanism and energy supply of transport sigma-1 receptor from endoplasmatic reticulum to plasmatic membrane. Sorry, here is mistake. This is very important to understand, because if we shall understand how it occurs, what's the basis of this mechanism, I think it will be big possibility to find a new medicine with neuroprotective properties. Thank you for your attention.